Okay, we looked at the dining philosopher problem. We saw a very simple semaphore based solution. We saw that it is not sufficient because it can help us with the deadlock part but not the starvation part. We said we will look at something better using monitors, right? So to remind you, a monitor is basically an upgraded version of the semaphore. It is an ADT, meaning you have your semaphore variable and you have specific functions which are the only functions you can perform on those variables. So you cannot do a random increment, decrement or whatever. If it says signal and wait, you can only do signal and wait. So in this case, we have pick up, put down and test. So these are the only functions you can do to your variables. We'll look at those in detail. First of all, what are our variables? We have an array state 5 units long to represent the 5 philosophers obviously, and the value each of these variables can take is thinking, hungry, eating. So enum is enumerated data type. Those of you who are familiar with C, which is technically supposed to be all of you, should know. So you're creating your own data type, you're specifying the range of values it can take. So this basically means you have an array, it's called state, 5 elements long representing the 5 philosophers. Each element can only have the values thinking, hungry or eating. You have another array called self, 5 elements long, and it contains condition variables. Condition variables are basically your semaphores where you can signal or wait. Those are the things you can do with them. What is this used for? This is what is going to help us deal with the starvation part. I'll tell you how. So the idea with any philosopher is they will pick up, they will eat, they will put down. Okay, makes sense. Simple, straightforward logic. You pick up, you eat, put down is the natural flow of things. But how exactly are these pick up and put down designed such that both deadlock and starvation are avoided? That's the question, and here is the answer. Enum, thinking, hungry, eating, state of 5, condition self of 5. These are the variables we are declaring, which I have just explained to you. I am sure that is clear. You have pick up, put down, and there's another function called test, all of which we will be looking at in a moment. We'll look at the initialization first. So initially, your state of I is set to thinking for all 5 philosophers. So basically, you have this state array for 5 philosophers, right? And it can have one of these 3 states. Initially, all of them are thinking. You're putting them in that state. Subsequently, they will move to the hungry and eating states and they'll come back to the thinking state. Initialization, we're making everyone belong to the thinking state. And self is a variable, self is an array full of semaphores. So initially, you can make it all zeros because no one is accessing anything. So yeah, that is fine. Now, the flow, as I said, is pick up, eat, put down, right? So we'll start with pick up. So if any philosopher is going to invoke the pickup function corresponding to them, I represents the philosopher number, obviously 0, 1, 2, 3, 4 or 1, 2, 3, 4, 5, however you want to call it. It will first set that person's state as hungry. So remember, initially everyone was thinking. Now this person wants to pick up his chopstick, meaning first his state will be set to hungry. Then he will call this test function. Test function will check for deadlocks. I'll come to it. So if the test function says there is no deadlock, he will be permitted to eat. So he will eat this. If thing, you won't even go into it. If the test function says deadlock, then if state of I is not equal to eating. So if the test function says there is some deadlock, or you have to wait. Basically, if the test function says someone else is using the chopstick which is accessible to you, hence you have to wait, then the state will be still in hungry, right? It won't have changed to eating. So self of I dot wait. So this self variable, we will call a wait on it. So why are we doing this? When you change the self variable, when you call a wait function on it, what it means is this person is ready to eat, okay, he's hungry, but resources are not available, so he is waiting. That is what this means. Now finally, let's say something happens and this state, whoever else had that chopstick had put it down. How is this person going to come to know? So we'll take a look at the test function now. So what happened, I will explain each of these functions and then I will also give you a full overview again, a recap kind of a thing. So if things are getting a little confusing here, it's alright, there's no need to get flustered. So yeah, pickup function basically the person would have been thinking, you change it to hungry, then you call the test function. What does the test function do? Check if my left side neighbor is not eating and I am hungry and my right side neighbor is not eating. All three of this should be true. This you can see, right? That person's state is not equal to eating, my state is hungry, and the other neighbor is also not equal to eating, then I am perfectly free to eat. So my state will be changed to eating and I will signal the self variable. So the self variable being signaled means, okay fine, this person is not waiting for anything anymore. Right, so that is what happens in the pickup part. So pickup part, first we set our state to hungry, then I call the test function. The test function will check neither of my neighbors is eating and I am hungry, which means I can pick up my chopstick and eat. So I will set my state as eating, meaning both my adjacent chopsticks are mine, and I will signal my self semaphore, meaning I am not waiting for anything, everything is fine on that front. Supposing one of these conditions is not true, either my left neighbor is eating or my right neighbor is eating, then this thing is not going to happen, right? So none of this will be executed. So after the test function is called, you come back here, state of I will not be equal to eating, because here you set the state as hungry. It goes here to the test function. If all this is true, the state changes to eating. If for some reason, if someone else is eating probably, then this is not going to be changed, so state is not equal to eating, then you will be waiting, correct? So that is what the pickup function does. Basically it's the same idea as your semaphores only. You want some resources, you are checking whether all of it is free. If it is all free, you are taking it up and you are marking your claim over the resources by setting your state to eating. If something is not free, you are waiting for it. The only thing is you are mentioning in this self semaphore that you are waiting, so that the moment someone else puts down, you will be informed. How will you be informed? We'll come to it. I was talking about put down, right? So this person wanted to pick up, they set their state to hungry, they tested it, whether they had to wait or not wait, somehow they finally got their chopsticks, they ate it. Now they want they ate their food, sorry. Now they want to put down the chopsticks. So for put down, first I will change my state back to thinking. So hungry is when you are waiting for the chopsticks, eating is when you are using the chopsticks to eat, and when you are neither hungry nor you want the resources, you are not doing anything, then you will be in thinking state. So that is what I want to be in right now. So I will put my state to thinking. Then I will test my right neighbor and left neighbor. So why am I doing this here? I can technically, in one sense, it looks like just this philosopher being very chivalrous, offering his chopstick once he is finished eating to the neighbor. But see, the thing is, here, this person was hungry, okay, and they set their state to hungry. They tested. If all these conditions were satisfied, neither of the neighbors was eating and this person was hungry, they would have immediately gotten access, they would have eaten, they would have put it down, fair. But if someone here had been eating, so this person was waiting, then this guy who was eating here, he'll finish eating and he'll put the chopstick away. But how does this guy who's waiting know that my neighbor has put the chopstick down, it is available to me? So in some previous example, we saw this thing called a wake up function, right? So when one person is finished with the resource and is going, they do a wake up kind of a thing to one of the guys who's waiting. That is exactly what. So when I finish eating, I will call the test function for both my left neighbor and right neighbor, so that if they had been waiting because I was using the chopstick, then now they will be notified. The signal will go to their self semaphore. They will be able to use the chopstick. So this is how we are able to deal with the starvation part. See, the moment you use a semaphore, most likely deadlock is going to be out of the question. Semaphores are pretty good at handling deadlock. Starvation was the problem here. So adhikku what we are doing is, every time someone finishes eating and puts their chopsticks down, they are going to check upon both their neighbors. Were you waiting because of me? Were you waiting because of me? If yes, immediately the thing goes there. So one quick note I would like to draw to your attention is, that is why you have this middle condition, state of I equal to hungry. Because see, if someone is calling the test function from here, they have already set their state to hungry. So you don't need to check that condition here if it is being invoked from pickup. But if it is being invoked from put down, then it makes sense, right? Let's say I was eating. I have two neighbors. My right neighbor was hungry, but he was waiting for me to finish with the chopstick. My left neighbor was not hungry at all. He was thinking only. So why should I offer my chopstick to the left neighbor when he doesn't need it? That is why when I call the test function from here, this condition also needs to be checked. That is why this middle condition is there in the if. Alright. So I'll recap. Don't worry if that was too much information. I hope you know what the dining philosopher problem is. And the problem with semaphore is deadlock solve, starvation will not be solved, right? So what we're doing is we have two arrays, state of 5, self of 5. 5 because 5 philosophers. State can represent any of these three values. Self is just a semaphore. It will tell you whether this person is hungry and waiting for chopsticks or not. Avladha, simple. Now each philosopher will first pick up, then they will eat, then they will put down. So how does this pickup happen? You first set your state to hungry, then you check for both of your neighbors. If both left neighbor is not eating and right neighbor is not eating and I am hungry, then I will set my state to eating. I will signal my self variable to ensure that everything is good. Then I will eat. So state of I is not equal to eating. Because I set it equal to eating here, this part is going to be false. Nothing happens. I will just eat. Then I will put down. Supposing when I test someone else was eating, then this part will not be executed because this condition becomes false. So I will come here. My state has not been changed to eating. It is still in hungry. So I will signal myself to wait. I know you're hungry, but the chopsticks are with someone else. Let us wait. Now, once someone who has finished eating wants to put it down, they will first change their state to thinking. Then they will test for their left neighbor and right neighbor. So when they test for that neighbor, they'll see if that neighbor is hungry, and again the other neighbor as well as I, both of us have finished eating. That person's state will be set to eating, and this signal. So this signal, self of I dot signal, is how someone who is waiting for a chopstick comes to know that the chopstick is available. So again, how does this solve starvation and deadlock? As soon as I finish eating, I am going to offer my chopstick to both my adjacent neighbors, and if either of them wants it, they are going to take it. So starvation will not happen. As for deadlock, we are using a semaphore / monitor based structure where you pick up, you use, you put down. So the whole idea of a deadlock is out of the question, right? The semaphores by nature are designed generally in such a way that they help you avoid the deadlock situation. So that's it about the dining philosopher problem and how monitors help to solve them. Thank you.